Hello everyone, welcome to MES e-learning studio. Today we are going to talk about homogeneous linear differential equation of higher order with constant coefficients. So first of all, let us understand the meaning of this term. What is the meaning of homogeneous linear differential equation of higher order differential equation with constant coefficient? Let me write one equation. Suppose we have equation a naught dny over dxn plus a1 dn minus 1y over dxn minus 1 plus a2 dn minus 2y over dxn minus 2 and so on. This is a and y equals to 0, where a naught, a1, a2 are up to an are some constants. These are nothing but some constants. Then such equation is known as homogeneous linear differential equation of higher order with constant coefficient. Why we are saying this equation is a linear differential equation? As we observe that each and every derivative, since we have dny nth order derivative of y, n minus 1th order derivative of y and all, since all the terms are having degree 1, so I will say this is linear differential equation and this is the higher order, like we have nth order, n minus 1, n minus 2 and so on. Since we have these are some constants, so which indicates constant coefficients. Homogeneous linear, since we have degree of each and every term present in the equation is 1, so this is homogeneous linear differential equation and it has constant coefficients, so it would be homogeneous linear differential equation with constant coefficients. Now the question arises how to solve these equations. Suppose I want to solve this equation, so I would say general solution. How to find general solution in this case? So first of all, I'll convert this, or I would say y equals to some solution. How to find this solution? For this, I need to find the auxiliary equation. So first of all, I'll form auxiliary equation. How to make auxiliary equation? We'll put d over dx equals to m in equation number 1. So if I'm putting d over dx equals to m, that equation number 1 becomes, it is a naught, so you will write a naught. Here we have nth order derivative, so you will write mn plus a1 m raised to n minus 1 plus a2 m raised to n minus 2 and so on. The last one would be an, and we'll put this term equals to 0. This would be some polynomial in m. Once we will solve this, we'll get the result in terms of n. On solving this, I'm going to get the value of m. It might be alpha 1, alpha 2, alpha 3 and so on, alpha n. Since this is a polynomial of degree n, so I would get n roots here. So now the nature of root will decide which formula is applicable. Now the nature of roots will decide how to find the solution. For example, we know that we have suppose alpha 1, alpha 2 and so on, alpha n. These are n roots. If these roots are real as well as distinct, then we will find, normally actually we used to find complementary function. Then the formula for the complementary function would be, we will write CF, which is complementary function. So for each and every root you will take one constant, introduce one constant, and then the formula would be alpha 1 x. For second root you will introduce second constant and then you will write e raised to alpha 2x and so on. For the nth one, I'll introduce nth number constant and we will write alpha n x. So which is the formula for CF when our roots are real and distinct. Once we get CF, which stands for complementary function. CF stands for complementary function, then general solution in this case, then general solution would be y equals to CF. So I can directly write the final answer as general solution of the given equation is given by C1 e raised to alpha 1x plus C2 e raised to alpha 2x and so on, Cn e raised to alpha n x. So which is the formula for general solution, or I can say the final solution for the equation whenever we have the roots which are real and distinct. Now case number 2 is when we have roots are real and repeated. So we have roots like, if I am saying m, so it can be alpha 1, then the formula for CF would be, you can write C1 plus, for the second root you will introduce x, for third we can introduce x square and so on. Since we have n roots, so I would write C is x raised to n minus 1 and e raised to alpha 1x, which is the formula for CF. In this case, y equals to, if I am saying general solution, so it would be y equals to CF, and then we can write the same thing. Let me move to the next case, which is case number 3. When our roots are imaginary, it means if we are finding the roots and the roots are in the form alpha plus minus I beta, I am taking 2 roots only here to explain. Suppose we have roots like alpha plus minus I beta, where we know that alpha and beta both are real. So we have roots like this, so we can use formula. Then the formula for CF, where CF stands for complementary function, so we can write e raised to alpha x C1 cos of beta x plus C2 sin beta x, and then we can find general solution, which is y equals to CF. So we can write this and we can get the final solution in case we have homogeneous equation. Now let me move to next case, which is case number 4. Suppose our roots are repeated imaginary. I would say m is alpha plus minus I beta and alpha plus minus I beta. I can see if we have fourth order equation, and after solving that equation we are getting the same roots, then the formula for the CF should be, CF will be, we will use, like we have written this, so we will introduce 2 new constants. I'll write e raised to alpha x, then here we will write C1 plus C2x cos of beta x plus, let me introduce new constants for sin beta, so here we will write C3 plus C4x sin of beta x. So that would be the formula for CF, and hence we can find the general solution, which is y equals to CF. Now case number 5, how to find the CF if we have different kind of roots, like roots are of the type we have solved and the roots are like this, where alpha and beta both are real. In this case, formula for complementary function would be e raised to alpha x C1 cos hyperbolic beta x plus C2 sin hyperbolic beta x. We can use this formula, otherwise we have one more formula. I can write C1 e raised to alpha x cos hyperbolic beta x plus of C2. We can use this formula to find CF, and hence we can find the general solution by y equals to CF. So let us take some problems based on that. Number 1, this is the problem and we need to solve this problem. First of all, I will check whether this equation is linear differential equation with constant coefficient or not. Number 1, I can see it is third order derivative and the degree of this is 1, where this is second order derivative where the degree is 1. This is first order derivative and the degree is 1. So this is a linear differential equation and it has coefficients as minus 2 plus 1 and 1. So I'll say this equation is homogeneous linear differential equation with constant coefficient. Since this is homogeneous, why it is homogeneous? Because right hand side term is 0. So I would say this is a homogeneous linear differential equation with constant coefficient. Now we need to solve this. For solution, what we need to do, we'll just put d equals to m in equation number 1 and form auxiliary equation. When we are replacing d by m in equation number 1, you will get m cube plus of m square minus of 2m equals to 0. We can solve this equation and get the values of m, which are known as roots. So I'll take m common. So you will get m square plus m minus 2, which is 0. So if I'll factorize this, or by splitting the middle term, you will get m. If you want, you just write 2m minus m minus 2, which is 0. Now we can take m common. Here I can take 1 common. So you will get m plus 2 and m minus 1, which is 0. So now we have 3 factors equals to 0, which is giving me the values are 0, 1 and minus 2. Now I need to check the nature of the roots. Since these roots are real numbers as well as it is distinct, now case number 1 is applicable. Roots are real and distinct. So you can find complementary function, which is given by, you will introduce constant c1 and e raised to m1x, where my root is 0. So we will write 0x. Second is c2 e raised to 1x, and third would be c3 e raised to minus 2x. Let me rewrite it again in such a way. Since this is e raised to 0, I would write 1, and this is c2 e raised to 1x stands for e raised to x, and this is c3 e raised to minus of 2x. This is my CF. Since right hand side is 0, so PI is 0. So I can write general solution is given by y equals to CF, and y would be c1 plus c2 e raised to x, c3 e raised to minus 2x. In this way we can solve the equations, right? Let us take some another example. Here I have taken question number 2, which is d square y plus 6dy plus 9y equals to 0, and we need to solve this equation. Number 1, I need to check which type of equation is this. I can see that it is a higher order derivative, like second, third one, and without derivative, that is term, and degree of each and every term is 1. So this is linear differential equation. Since it has constant coefficients, so I would say this is linear differential equation with constant coefficient. Now we will solve this equation in the similar pattern. So let me put d equals to m in equation number 1. In equation number 1, when we are putting d equals to m, so you will write m square plus 6m plus 9 equals to 0. Since right hand side is 0, so you would say this is a homogeneous linear differential equation with constant coefficient, because the right hand side term is 0. Whenever we have right hand side term is 0 in this equation, so we would say this is a homogeneous linear differential equation with constant coefficient. Can we factorize this? I can observe that this is m plus 3 whole square. So let me rewrite it like this, which is giving me roots like minus 3 and minus 3. Now I need to check the nature of the roots. Since these roots are real number, but it is repeated, so I would say roots are real and repeated, or repeated real, we can write. So these are repeated real numbers. So CF, let me find complementary function. So it would be, for first value I'll take C1, for second we will introduce new constant with x, and e raised to mx means minus 3x. So we are done with the C complementary function. Let us find general solution. So general solution would be y equals to CF, as right hand side is 0. So there is no PI. Right? So y equals to c1 plus c2x e raised to minus 3x would be the general solution of the given problem. In this way we can solve the problems based on linear differential equation with constant coefficients. Thank you.